Have you ever wondered how engineers determine the balance point of complex 3D objects? In this lesson, we will use calculus to find the centroid of a solid of revolution, a crucial calculation for structural stability and physics. When we rotate a 2D area around an axis, we create a 3D solid. Because of the symmetry of rotation around the x-axis, the centroid must lie on that axis. Our goal is to find the exact horizontal coordinate, x-bar. Due to rotational symmetry, the center of mass in the vertical and depth directions is 0. This simplifies our work significantly, as we only need to solve for the x-coordinate using the principles of moments and volume. To find the centroid, we imagine slicing the solid into infinitely thin disks. Each disk has a volume, dv, equal to pi times the radius squared times the thickness dx. This disk represents a tiny portion of the total mass. The x-coordinate of the centroid is the weighted average of the x positions of all these disks. We calculate this by dividing the integral of x times dv by the total volume of the solid. By substituting our expression for dv into the centroid formula, the constant pi appears in both the numerator and the denominator. We can cancel it out, leaving us with a ratio of two integrals involving our function f, x. The numerator represents the total moment of the solid about the y-axis. It accounts for how far each piece of volume is from the origin. The further a section is, the more it pulls for the centroid toward it. Let's apply this to a practical example, a cone. We can generate a cone by rotating a straight line, y equals r over h times x, around the x-axis from 0 to the height, h. First, we set up our two integrals. The volume integral uses the square of our function, while the moment integral includes an extra factor of x. Both are evaluated from the vertex at 0 to the base at h. Integrating x squared gives us x cubed over 3. When we evaluate this from 0 to h, we arrive at the familiar formula for the volume of a cone, 1/3 pi times radius squared times height. Next, we solve the moment integral. Integrating x cubed gives us x to the 4th over 4. Evaluating this at h results in a moment of 1/4 pi times radius squared times height squared. Now we divide the moment by the volume. The constants cancel out beautifully, leaving us with 3/4 h. This means the centroid of any cone is located 3/4 of the way from the vertex to the base. Let's try a different shape. Consider a paraboloid formed by rotating y equals the square root of x from 0 to 4. This shape is blunter than a cone, so we expect the centroid to be different. Squaring the square root of x simplifies our integrand to just x. Our ratio becomes the integral of x squared divided by the integral of x. This is much simpler to solve than the cone example. After evaluating the definite integrals, we find the centroid is at 8/3, or approximately 2.67. This is further to the right than the midpoint, reflecting the fact that the volume grows as x increases. To summarize, always remember that the centroid is the ratio of the first moment of volume to the total volume. Use the symmetry of the axis of revolution to eliminate unnecessary calculations for the other coordinates. Quick test: for a cylinder of length 5, where would the centroid be? Since a cylinder has uniform thickness, it sits exactly in the middle at 2.5. Thank you for learning with us today. Generated by Vision Solve AI.